because a couple of people mentioned that they really want to, uh, uh, that I have the function to record this. Oh, it's recording right now, actually. It's not bad, you know.
You're seeing the red of my screen. Let me get it to share here.
Yeah, your screen is here. All right, this is the big screen. Okay, I think we can get started. Well,
Okay.
good morning. I think most of us are good morning. Well, thank you so much for attending the first, UD mobility in this academic year. So we are extremely happy to have Sean Davis from Red Hat. So I assume that if you are in computer science, even you are not in computer science, we should all know Red Hat, right? So that so Sean is currently the director of engineering responsible for the automotive and the edge. I like this too because edge computing is something we have been working for a while, and then autonomous connected vehicles is also an area that we are actively working on. So I got to know Sean probably earlier this year, and then I'm so happy that to see Red Hat is interesting, have been pushing for the OS level kind of support. I think that is something is missing because I working in this area and stay in state of Michigan. We have a chance talking to many OEMs and potential suppliers. Well, they most of it interesting on the sensors, algorithms, and the stuff. But the reality is, as a mobile computing platform, we all vision in that way for the future vehicles, and then you really need an operating system, so that they can support in the safety, security, and among many other things. So without further ado, let's welcome Sean Davis from Red Hat to share about that his journey and his vision in this area. Thank you, Sean.
Yeah, very good. Thank you. So yeah, as mentioned, my name's Sean Davis. I've been at Red Hat now almost 2 years as we had started to kick off this automotive initiative that we're going to go into today. Before that, I came from the automotive semiconductor space and then large software before that. So I've kind of bounced back and forth between hardware and software, but almost always staying in the automotive space. It's kind of what gets me excited. So obviously, I'm very excited about what we're doing at Red Hat. And so let me give you an introduction into what that looks like. And so why would a enterprise software company like Red Hat feel like it would be a good idea to get into automotive? Well, I think the general consensus in the industry is that it's going through a pretty significant set of transformation. And looking at that and looking at what Red Hat did historically in the enterprise software for the data center space, in terms of transitioning from Unix to Linux and being a major platform that standardizes the way things are done, there's some similarities to that transformation that we see, and it makes sense for us to start to look at that. And so I'll take one step back from automotive there. That's the tease, but we're doing more than just automotive. It's about edge computing as well, as Dr. Shi mentioned. So Red Hat looks at edge in many different ways. And you can see here, I won't spend a lot of time on this or read it out to you, but essentially we have the enterprise data center that we know and are a leader in, and we're trying to find the areas that connect to that as you get further away from the data center and with smaller computing power. And so the areas that looks like is industrial and things where there's automation and manufacturing, things of that nature. There's also telecom, where you have a level of compute at towers that is separate from the data center. And so you'll see these are getting from big to a little bit smaller to a little bit smaller. And then the smallest, which is where I spend most of my time, is on the consumer edge definition, which is automotive, obviously, but also other edge computing things that are the smallest and most embedded. And that may not be even just consumers. It could be also government elements or drones or vehicles of that nature as well. So it's really, that just means getting down to the most embedded devices. And so you can trace our journey as doing edge computing that meant the data center, and now we've moved into the telecom and in vehicle, and then in the future, even more embedded where things are happening, on points of sale or industrial control systems, things like that, where people are doing application specific on more generalized hardware that includes things like safety critical systems like automotive or medical devices or beyond. So edge gets lots of definitions, even internally at Red Hat. You ask one person what they think edge is, and they'll give you a different answer. So we're feeling out the ways that we think we can provide assistance in formulating a more standardized approach to such a complicated industry. And so getting back to automotive, what we see this looks like is that some of that shifting that is going on at the OEM level, where there's the old way, which is a standalone vehicle that has some hardware and software. And then the next generation was some connectivity, services like OnStar or map updates or even software updates. It comes after that, where you can then have a connected vehicle that's giving you a improving experience over time, as opposed to just services delivered to the vehicle. And then the big buzzword of the day today is moving into the software-defined vehicle and what that means. And we'll talk a little bit about what that looks like. So another fundamental change outside of what the goals of the industry is in terms of connectivity is the overall hardware compute platform. So the traditional way is, in order to provide hardware segmentation, mostly from a safety need, as well as being able to farm out components to various providers or tier ones, they would be individual computing components that are lots of small elements that get connected together. That's the old way. So what we see now is the new way is both somewhat because of the semiconductor shortage that happened a few years ago, where if any one of those ECUs wasn't available, the car couldn't ship. Well, how do you depend less on a multitude of vendors? Well, you start to consolidate some of your hardware. But you can imagine if one of the primary goals of having lots of separate discrete components was segmentation at the hardware level, when you start combining them into a single computing platform, you run with a new segmentation problem where you've got to do it in software. And so that's why you see a lot of conversation about how software can be better segmented to provide that necessary function in a single high-performance computing platform with some satellite ECUs. So that's kind of a change in hardware architecture we're seeing, which feeds well into the path we followed on the data center, getting to more ubiquitous, powerful computing to perform multiple operations at the same time for different needs. And so it's starting to look similar. So what do we do to address that? Well, we think if we provide a solution that connects an in-vehicle operating system to our data center capability, now we provide a nice combination for the automotive industry of being able to do things like rapid development and testing in the cloud, or deployment to the vehicle of the elements that were tested on the cloud, offering connected vehicle services related to the cloud components we have, as well as some of that edge that is at manufacturing. When you're building the vehicles, a lot of what the automotive industry is about manufacturing as well. And so then we could provide help there. And so we really view this as a working with Red Hat, we can provide assistance in modernizing a lot of the aspects of the automotive industry. And then obviously the area we're going to focus on today is the in-vehicle portion. So what is our mission for that? We want to have it be open. Red Hat, if you don't know, is an open source company, if not the open source company in terms of participation in open source upstream projects, particularly based on Linux, but also things that build upon that stable base that Linux is. We want it to be safe. And so one of the fundamental aspects of an in-vehicle operating system is it needs to provide functional safety support for applications that require it in order to make Linux more than just an infotainment offering. It needs to be secure, obviously, with connected vehicles. That adds new attack vectors, and we want to make sure that the capability that is built into the data center for Linux for security because of mission critical software for banking or people's personal lives is there and secure. We want that same level of scrutiny to be possible for the vehicle. And so these things all can make sense together as a way that we can provide something new, something more standardized, and yet enabling less wasteful engineering work to generate unique OS builds for every single platform within that mix of ECUs, and try to get things more towards that data center-like model of big, powerful computing that can be segmented to provide multiple operations. And some of those would be ADAS, which is driver assistance, digital cockpit, which is about infotainment, but as well as the digital cluster that shows your speedometer that has some safety requirements to it as well. Body control, connectivity, telemetry, things like that. Lots of the computing areas of the vehicle we think this makes sense for, with different applications of the vast amount of software that Linux brings to the table. So here's a quick software stack look. We're focused on the operating system. There's opportunities for middleware and applications on top. So we're not looking to swallow the whole industry, of course. We're looking to provide that stable platform that it really enables the industry to tap into innovation as opposed to get stuck in wasteful engineering that slows the whole process down. And again, as I mentioned, having a stable platform provides faster time to market for the car makers. They can innovate and iterate more quickly because they have better tools for doing their development. They're not relying on 15 different build tool chains from the various embedded manufacturers. They can use standard CI, they can use standard build processes that Linux brings to the table, and they can tap into a broad set of expertise. We do expect the OEMs that we work with are having challenges hiring computer science candidates coming out of school for some of the software that they're building, and getting more of that software to look like modern software the industry is familiar with from a software standpoint means you have a better chance of finding the talent that you need to be able to build the software that you need more fast. That helps with CI and continuous development. You get faster productivity. It also makes it more supportable, which is a key aspect of the vehicles when they're needing to operate for 15 or 20 years. Being able to then turn fixes on a standard set of hardware helps, as opposed to keeping racks of bespoke hardware in a warehouse that you have to pull out 15 years later to fix a bug that you found. And again, going towards these standards that migrate more readily to fix bugs in the open means you get a better chance to have long-term relevancy. So, sounds really great. From a business standpoint, let's look at how we do this technically. So what is the Red Hat in-vehicle operating system if it's still really just Linux? Well, there are some things you have to add to it in order to make it relevant in that space. So it's got to have a kernel. That's not a surprise, but we're adding real-time capability to it. We expect, because of that need for software segmentation, we want to have a container runtime, but the container runtimes like Kubernetes that are existing in the data center are massive and not necessarily appropriate for what we would want to have in an embedded system, nor given some of the weaknesses they have in terms of eventual consistency, which we can talk about in a bit, where you need much more predictable capability in a vehicle to make it safe. We want to be able to add over-the-air updates and security updates, and Linux has lots of ways that you can provide incremental updates to the operating system, as opposed to some of the other in-use operating system options in the industry where you basically reflash the entire system. We can actually do sequential small patch updates and then A/B switches back and forth between different versions if there's an issue. And so it provides a lot more capability there already out of the box. Obviously, need for monitoring and diagnostics. That stuff all exists in Linux, so it's easy. The tool set I mentioned before, building for Linux, is a well-solved problem with open tools that can be scaled to large organizations in build farms, as opposed to having to have super capable or custom bespoke hardware on every engineer's desk. That's a great accelerant for the development process. We need to have failure detection and control, obviously, in looking for unexpected behavior. We need to have that for the safety aspects. We need to have mixed criticality support. That's a way of saying the same points I said in the container runtime, but it needs to go down deeper into the kernel and potentially virtualization in order to allow different operating systems to be present. You can imagine it's very familiar these days to have Android in your car or Apple's equivalent in the car in order to be able to connect your phone for media and mapping and things of that nature. Well, if that OS is already running, what do you do about having a safe Linux? Well, you've got to have ways that you can split between the non-critical workloads and the safety critical workloads, and that's what mixed criticality means. Linux is traditionally not something that's been optimized for boot speed, because in the data center, when you're running thousands of servers and you have multiple virtual machines running different versions of it, bringing up and down new instances is not something you really need to do quickly, because the data center is up and running, and then it's more about solving issues as they come, as opposed to something that constantly reboots as the primary path to use. Well, in a car, you turn it on and everything starts up. So there's industry requirements that have to be met in order to meet boot time expectations for things like media or chimes or backup cameras. And so we have to do some work on Linux to give it a way to be able to boot faster, or at least to boot certain functionality faster. And so that's kind of the general stuff. You can see there's some red elements for functional safety. Obviously, that's a critical aspect of working in the vehicle space. And so that takes the two forms. There's the material we produce to help our customers understand how to use the OS safely. There's also a additive element we need to create, which is called continuous certification, because we don't want to fork and freeze. And that's the traditional method, is minimize the amount of code that's changing in order to be able to minimize the amount of safety-related review work you have to do. But that cuts you off of the innovation of Linux and open source. And so in order to be able to stay up to date, get those safety fixes when they come, those security fixes when they come from the broader industry, we need to be able to get that certification done very quickly. And so continuous certification is basically a collection of tool chains and testing and other argumentation related to the certification that enables us to do that on a rapid pace, every release, if not every build, so that we can maintain the pace of innovation and keep up with what Linux is doing. So we have a publicly available version of the code we're doing. Again, open source company, we are upstream first. We have the CentOS automotive stream distribution. That is live now. It has all the code that is going into the Red Hat in-vehicle operating system. The only caveat is those safety certification elements are removed, because we have to do work to produce that for every official in-vehicle operating system released to customers. But as an academic institution, you're welcome to join that the CentOS SIG for automotive and get involved with that code today. There's no restrictions. Go take a look at it, start to contribute to it, engage with us. We're happy to have it. That's what we're about with the way we do the upstream engagement with communities. So we're trying to build this community of automotive interested parties, both customers, academics, ourselves, in order to really further the ability to do innovation in this space. So that's the high level view. Let's dig one level down and look at some of the specifics. So I talked about the adding real time to the kernel. Well, we're using the preempt RT patch set that's been around a while, but it actually hasn't been merged into the mainline kernel for quite some time as it's getting done. That's going to happen soon. And it doesn't really make it hard real time. So if you're hearing real time and saying, wow, Linux being real time, that's not what I would have expected. You're right. It's actually just adding some specific capability for preemption so that critical processes can get access to the kernel when it needs it. And it prevents some of the priority inversion delay problems that you might have without it. And so it's a tunable set of patches that enables you to make sure the system responds fast enough to the critical processes that you need it to. So it is like it's real time, even if technically it's not hard real time. Now, what we see is we can get the max latency on a ARM SoC down to about 50 microseconds, where you'd see orders of magnitude higher on a typical system without the RT patch set. So it's functional, but it is tunable, so you can adjust that. Do you want more consistency? Do you want more reduction in max latency? That's what you can tune. And that ends up being a different build configuration that we're deviating from the enterprise system. We've also added the runtime verification feature that's been checked in the open into the kernel, and provides a way to make sure and confirm that deadlines are met. And so one of those aspects of functional safety, if you're not familiar with it, is you have an expected behavior, you have some software that's intended to operate on that behavior, and then you need a way to make sure that that behavior is happening as expected. And so this runtime verification feature that we created and checked in to the upstream kernel gives you the ability to monitor what's going on and see that the real time is working as expected. All right, let's talk about virtualization. So I talked about needing to have maybe Android or Apple in place on the same SoC as the one running the safety critical system. So that would, in the traditional sense, be done with a hypervisor. And so the industry typically likes type 1 hypervisors that are very low level, and they're not tied to an operating system. And so you'll build the various OS instances on top of that hypervisor. And that hypervisor is the first piece of software after the basic bootloader that gets running, and it then instantiates the various operating systems it needs to. That's the traditional way. We're looking at moving into type 2 hypervisors, which are hosted as part of the operating system itself. So in this case, Linux would boot first, and then it would be able to then load the other instances of operating systems as needed. And that's a different take, but we have a lot of experience with KVM in the enterprise space, and we think that's a equally selectable way of doing this, and it has some advantages when it comes to the safety aspect, because you don't have to have as much interaction between a safety hypervisor and then a safety OS, which sort of spreads the expectations around, where you can have a safe OS that then is hosting your unsafe software in QM on top of it. So that's what that looks like. The traditional way is hypervisor loads, you get guest OSs and workloads. The new way you can see on the right is the host OS loads, and then it runs the type 2 hypervisor within it, and then it sequesters the guest OS on it, but also can still run native code in the OS itself. And so that gives us more options to address some of the safety and mixed criticality. And so you can see the long-term plan here is one of providing for options within the digital cockpit space. Yes, you could run a type 1 hypervisor and you could run the OS on top. That's still supported. But we also think it would be helpful to do both native apps, QM and ASIL-B. So you'd have to have the way to have freedom from interference for those safety critical applications in the OS, in the kernel, essentially. Then offer that hypervisor to run QM apps like Android, and then have containers as well. And so I talked about that as something we're adding, that you could also provide segmentation for QM and ASIL applications of containers. So providing options, not one solution is necessarily right for every situation. And so again, being a standardized platform, this gives the tools that we think the industry needs to make progress on them. So I mentioned containers, let's talk about it. The requirements for it is consistency. And so I mentioned that before. Kubernetes and K3S has eventual determinism and eventual consistency. So you ask it to do something and it will get there. But how long it takes to get there and what might happen between then is not necessarily understood. And that's not as important in the data center, because you've got lots of parallel processing going on, and there's not as much safety critical aspects or time critical aspects until the application's up and running. Well, when you're in the vehicle and you want to use containers to segment various states, let's say you're in the backup camera mode, that might be one state, and you're driving in an autonomous mode, that's another state. You're driving outside the autonomous mode, that's another state. And so you might want to load those software modules in a container and then dispose of them as they're no longer needed to provide computing power in your overall system for something else. But those transitions are pretty critical. That needs to be very well understood, and the state you're going to end up in needs to be deterministic. And so classical containers, we don't think are appropriate. And so we need to make some changes. But we still want it to be standardized. So the vision would be you can still have someone who's familiar with Kubernetes and how to configure them and build them, but you could build our special type of container that's supported on, well, it's not even a special type of container. You can build the standard container that can run on our special type of orchestrator that runs in the vehicle. And it does that in a way that minimizes memory, disk, CPU, et cetera, for embedded system, still provides flexibility for access to the unique things about the car. But again, that predictability needs to be there in order to satisfy safety. And so this is the general architecture. I apologize, it's a little pixely. It used to be called Hirte, but we realized that was copyrighted. And so or trademarked, and part of the submitting it to the open was we need to rename it. So it's now called Blue Cheat. And that's in the auto, or it's actually in Eclipse SDV. We're submitting it to them to carry forward as a community that can continue to build and expand on this Blue Cheat capability. But essentially, you've got the ability to have multiple devices that are running the agent that controls it, the orchestrator, and within that, it utilizes systemd within the Linux system in order to control these containers coming up and down. So it operates containers like you're expecting, but it provides those key features that we need. So other things we've done to make it appropriate for automotive is making containers boot faster. You're sensing a theme here, I'm sure. Getting things to be in an operational state quickly is important. And we've posted some information about how we're maintaining compatibility to the cloud with the vision that if you can build your container and test your container in a cloud instance, then you can deploy it from that cloud to the device through the connected services. And then it's that same exact container that's operating on the vehicle. And so you get this very nice testable story that scales well for the car makers, but also provides that flexibility needed to run segmented dynamic workloads within the vehicle. Other things we've done in Linux itself, we've added a new file system integrity feature in order to provide a little more confidence and security in the file system itself from preventing it being overwritten accidentally or maliciously, which is something that you might traditionally do with hardware, but balancing the need to be able to do sequential updates of the software, you can't really lock the whole system down. And so this feature provides that intermediate necessary to be able to have the security and stability you need, but also be able to provide incremental updates rather than full flash updates every time you want to make an update, which again is helpful in that connected updates over time feature that is great. Instead of having to bring your car in for a recall and have someone connect a USB drive to it, now you just get it updated when you park it overnight, and a new update's available for you when it's needed. I mentioned before the runtime verification, that's here again, but we talked about it already, so I'll skip through. So that's sort of the core technical features. What's the real challenge here in enabling an operating system like Linux that has been built over 20 years, is designed for a different context, and is massive, particularly in its monolithic kernel? That does not necessarily align with functional safety, according to ISO 26262, which prescribes a development method that we're not following. It prescribes verification methods that aren't really appropriate for an OS like Linux, and has copious amounts of paperwork expected in order to be able to certify, which immediately gets in the way of the pace you need to be able to update it. Like I said before, continuous certification becomes a need, but the traditional process is so slow and particular that it means you have no choice but to freeze your code and support it as is for the lifetime of the product. And so what are we doing to try to get in front of that? Well, we're dealing with not a blank sheet of paper, we're dealing with existing software. And the standard just doesn't even comprehend that, because it was written in the mid to late 90s and updated more recently based on a progression of the industry from hardware-centric solutions to hardware with a little bit of embedded software to an embedded software solution. But now we're at high-end, high-performance computing. The standard didn't even comprehend that in the vehicle at the time. And so it's a challenge to align older thinking to a different hardware platform to this more modern take. And so that's what we're here trying to do. So what is our approach? So there's been many that have tried and failed to get Linux ISO 26262 certified. And what has boiled down to is the approach that's been taken time and time again is, well, there's this V model that the standard expects. Figure out your design, go down to the deep technical details, implement it, and then walk back up the other side of the V to verify them as you go from small units to subsystems to integration to the final thing. And have a paper trail of that entire thing with a linkage between every requirement leading to a test. So what people do is, well, if we're starting at the bottom of the V with implemented software and none of the other stuff exists, what do? Well, we start to try to revise history by generating the documentation that doesn't exist, and then we build a bunch of extra tests that address those requirements that we have synthetically created. Well, if you think about that, yes, it checks the boxes of the standard, but it also isn't really genuinely affecting the product because the product's already been built. And yes, you might get a little bit of extra verification out of it, but that seems you could skip directly to maybe we do some more verification without all of this extra paperwork that has to be meticulously maintained. And so we said, all right, we think that's not going to work. Honestly, we tried it for a little bit and we said, well, we definitely don't think this is going to work. And so what's unique about Red Hat, as I mentioned before, is we're the open source software company in that we have the largest percentage of our staff that are actually subsystem maintainers in the upstream projects that we utilize. And that's a fundamental aspect of how Red Hat does business, is we want to make sure we have experts who are participating consistently. We're not just a consumer of it, we are a participant in the upstream. That gives us a broad set of industry experts that are unique in their capability because they're the ones that are maintaining and interacting with other maintainers of this system and have been for many, many years. So we have this wealth of information available to us. So we said, okay, well, let's see what that does. And so we initially talked to those experts, where in a traditional safety approach, the safety team would be given a document that describes the architecture or shows some piece of code, and they would need to use analytical techniques to say, well, based on this diagram, here's how I think the system could fail, and here are the things we need to do to confirm that those failures won't occur. But we don't need to have a document that gets maintained or a diagram that may be overly simplistic or too detailed, which would throw off the safety analysis. We can just go directly and ask the critical question of the people that wrote the software and maintain the software to this day of where are the parts that are not sufficiently stable? Are there parts of this system that you would have concerns about? Are there some that are rigorously strong and are the best parts that we should look into, including in a safety space? How do you confirm that that is true? What are the methods you use? It's generally a different set of testing than what ISO 26262 provides. Okay, well then we have to figure out, is that testing sufficient? And so we work with them to understand what evidence we have that the existing process to make Linux stable enough for mission critical software in the data center, what of that could be useful to proving it's also stable enough and safe enough to be used in a safety critical application. And so then we look at that and we gather the evidence and we try to make a safety argument and we provide that to an outside assessor to tell us if that makes sense. And then we address open questions. Inevitably, we're not going to find a bulletproof argument from the beginning. And so we iterate on that to provide additional tools or additional material that we need to prove for those questions and iterate until we say, yes, we think this has a strong enough case to be proven already based on what's being done. Maybe that's not enough. Then we would take extra steps to say, okay, let's look at the traditional elements that ISO 26262 might provide. Should we just run them, even if they may not be our first choice because they weren't selected as part of how these open source projects were done? But maybe we build on top of that to just add an additional layering of safety and then see if that's sufficient. So again, it's this iterative process of working with our assessor to make sure that we're providing a better process, a better set of evidence that we're following that process, and in the end, a better maintainable, more safe piece of software, as opposed to a paper trail that looks like we did it, even when we didn't really think it through. So our goal is safety, not certification. And so then we tailor that into our safety concept and keep going. It's a continuous improvement process, which is what the standard guides you towards, as well as other quality standards like ASPICE and ISO 9001, where they are guiding continual improvement as an important aspect of maturity in an organization. So it sounds real simple. Just go ask some people some questions, see what you're doing, and then try to see if that makes sense. And it really is that simple at the highest levels. And then we get into the nuances of the requirements and the particular evidence and showing how the various things we're doing are actually providing security. So, for example, we've done this with glibc, some of the math functions. We have an expert who described the way verification is done on the math functions, and that we have a independent set of software that is implementing them from the glibc implementation that's used as a baseline to confirm when differences in behavior. We run them across many different platforms and look at the rounding variations that are occurring, and can target the optimizations for accuracy and speed to balance between those extremes within the library. And so it's not as easy as just saying, well, an addition should be an addition. Well, no, there's a lot more detail. But in a traditional safety approach, the diagram would say addition does this. Well, does it do that? And what could corrupt the memory that would prevent that from happening? What register access could cause the accumulator not to do the addition correctly? Let's go confirm those things. But instead, we have an entire set of material that is being done and has been done over years of iteration by the open source community that is both novel and more sophisticated than anything the standard conceived of 10 or 15 years ago. So we think that's a pretty good approach. What it means is we have to build a lot of explanation of how open source works in its processes. We have to continually look at the evidence that we're gathering and work with our assessor. We also think it's important to share this information, being an open source company, and we're looking at opportunities for publication to define various methodologies or describe existing methodologies that are being done within Linux in order to show how that is an appropriate tailoring for ISO 26262 compliance, even if it doesn't check all the boxes the standard had conceived. And so the goal is then to further the industry, get more people on board for how Linux and its associated platforms can assist in standardizing and get people involved. Then we do incremental qualification of subsections. So we're currently working on glibc. Next thing up is the kernel and subsystems of the kernel as well. And so we'll continually build that up as we go while trying to build that continuous certification capability. So yes, it's been certified once, but we need to turn the crank on a critical security update that came from industry. Fine, we'll just run it through this automated system again and resubmit, and we're good. And so we're very close with Exida. They're our primary partner for this. They're an industry leader in functional safety. So we're very happy working with them. And they're providing us a lot of good guidance on novel things that we should look at. So giving us the freedom to look away from the standard as written and instead look at the standard as intended, which is great. Just to list some of our kernel isolation things we're looking at. None of these are set in stone as the ways that we do it, but if you're a kernel person and you're interested in some of the technologies that exist there that we're looking at for isolation, both at the container and the kernel level, it's these existing features. We're not yet building new capability for this. We hope that we can rely on what's already there and operate it in a very specific way with guidance of usage. And that may be enough to provide the capability. It may not. That's part of this iterative process we're on, but those are some of the things we use. And again, as I mentioned before, we're big fans of partnering with industry and academia to engage in discussion, research. That's why I'm here today. Jointly publish, etc. Whatever method makes sense for those that are interested. But how we can solve this problem that the industry is suffering from that's holding back innovation because complex pre-existing software just doesn't have a well understood path to get used in a safety context, and enabling that wealth of software is going to be a huge accelerant for innovation, but again in a way that enables safety as opposed to just being cavalier like some automakers, I won't name names, might do, where they don't bother with safety and instead focus much more on innovation and the resulting problems that you would imagine are starting to be seen more readily. So we're presenting some of the thoughts we have that are more detailed about how we're looking at ISO 26262 with that glibc math I mentioned at the Exodus Symposium. That's in October. We also have a presentation about how we're looking at doing freedom from interference in the Linux kernel. We're also very active in communities such as ELISA, which is enabling Linux and safe applications, as well as we have the chair of the ISO PAS 8926, which is a separate update to ISO 26262 that is really focused on trying to better enable pre-existing software and set some of the ground rules for how that needs to be done. So interested in seeing your questions, of course, but also your future participation if this is something of interest. So I'll pause there and turn it over to Dr. Shi or others if you have questions.
Thank you so much, Sean. This is great. Now we have some time, we want to have more interactive discussions here. Do you,
Sure.
If you have any questions, since we don't have, a lot of people here, it's pretty good. We have, if you have any questions, just unmute yourself and go ahead and ask.
Hi, Sean. I have one question.
Yeah.
Hey, this is Xin. I'm a system professor from the University of Delaware. My students actually here, so you got more audience here.
Great.
So
Thank you.
Thank you for the talk. It's very interesting. I have one question because you mentioned the container a lot.
Yes.
I believe at the very beginning in the page 10, page 11, the container looks like you are building container on top of the KVM hypervisor. So I thought it's essentially a virtual machine, not let's say a traditional container. But later in the page 39 or 37, it showed a bunch of Linux kernel features that enables container. So I'm wondering what exactly approach you guys are using. Is that a bare metal container or maybe essentially it's a virtual machine? What kind of sandbox are you using, and what's your plan in the future?
Yeah, so it's actually two features. So I pulled up the diagram again, hopefully to make it more clear. So yes, we offer virtualization as a way to provide segmentation and to load things like Android as a guest OS or others. But it's not dependent on KVM to run containers. That has its own orchestrator that is based out of Podman, which is the container orchestrator that we use at Red Hat for all levels of containers. We have containers for data center, for edge, for auto, with different variations of what capability and how they're orchestrated. And the unique one that we're building for automotive is basically operated by systemd plus Podman components. So Podman launches, Podman starts up the container, Podman shuts down, and then systemd does the rest of the management from there. So it does not rely on KVM.
I see. So do you guys, is this container open sourced? Because when you run container like bare metal directly on top of the kernel, I feel the isolation issue has remained a long-term discussion on whether the isolation is good enough for running all kinds of applications. I'm wondering, is there any actual isolation mechanisms you guys have added to this container, or is there any other plan?
So I'll go back to that list of elements that I showed you before. These are the features that exist in Linux today, and the way Podman works for providing segmentation for its containers utilizes specific configurations of these features. The same would be the default configuration for our version of Blue Chi running in the automotive space, using a potentially different configuration but the same features. You're right. The question is that going to be enough to argue true freedom from interference of the QM application running in one container versus the ASIL application running in another? We have to prove that. We haven't done so yet. But the technology to initialize and manage the containers exists. It is open source. Nothing that we do is proprietary. So if I said we have a feature, it's open source. And so you can get at it by way of that auto stream distribution with CentOS. So you're right. It's not there. It's not done where we say, yes, we have proven this. That is what we intend to do over the course of our certification process. And we may find that, okay, containers are still viable for segmenting work and providing a dynamic configuration of discretely testable applications, but maybe they can't be ASIL applications if we can't prove the necessary freedom from interference. And then we rely on an argument within the kernel itself to provide bare metal applications that can be ASIL or virtualized applications. Again, by having all three options, our intent is to prove how you can do it with any of them, but we may find that some of them aren't enough. And if we have only one, that might be our starting point. And then the intent would be to grow from there to provide the necessary additional functionality. We're always contributing to Linux. So if we need to add another feature that actually provides that freedom from interference at the container level, sure, of course, we're going to try to do that as well.
Okay, thank you. Last question. So from my view here, if you only use those kernel features, they are definitely not enough. And you mentioned that you can run the Red Hat container on cloud, and once you deploy it on the cloud, you are able to deploy on the edge or automotive systems. Yes. So if we want to test it, we simply run it on top of our own server. That'd be good enough, right?
Yeah, that's the intent. Is you can build your container, you run it on an ARM server so that it's an ARM build, and then you could deploy it to the ARM device that has the Automotive OS on it, and the container itself is compatible, even if the orchestrator is slightly different, where the data center one is more feature rich, but you don't need that on the Automotive OS.
Okay, gotcha. Thank you so much.
Okay. One of my students is working on the real-time, scheduling, and in particular is on the operating system for autonomous, for the future vehicles. As you mentioned, you have this, some of them is a hard, real-time deadline. Some of them is less. And then, do you think that CentOS, the platform now, Red Hat is a good place so that he can plug in some of the his research on the scheduling, because right now what he's doing, I know Tianzi is here, so you can ask yourself. So right now what he's doing is using ROS too. So we want to hear from your input. I know ROS 2 and Linux, is there's a big difference in terms of architecture here. So what's your thought that?
Yeah, I'd say there is industry interest in ROS when you need that hard real-time capability. And so part of the value of having a virtualization option is we can run an instance of ROS for the real-time elements, even if it's running on top of Linux, given the type 2 hypervisor situation. You could flip it around and say, well, we really want a type 1 hypervisor, which is the traditional way, and have the hypervisor below Linux, letting ROS run for those hard real-time elements, and then have Linux in the system for other activities that don't need that critical time control. So yes, I think you're right. It's a great place to do research on it. I think at some point we would like to see ROS as a supported component within the auto stream distribution so that others who are interested in that can explore it. So if you're looking for a home, I think we would welcome that, and would love to see what you're thinking and how you're determining where the limits of the scheduling within Linux might be, if that's what you're looking at, and why ROS is necessary. But I expect there's going to be instances where both options might be the right choice, but I don't think we're intending to eliminate true real time. We just want to make sure the system that we build has the capability to still incorporate that. And that's why the hypervisor options exist, so that if you really need it, you can load it. And we also see in some of the multi-core systems, there might be a safety island that has its own real-time operating system instead. And it's segmented away at hardware level. So like I said before, the traditional way was lots of separate hardware elements moving towards more central compute. That doesn't remove all of the discrete hardware components. And so there's definitely still a reason to have real-time operating systems. They're very small that can run on these other safety critical elements that might exist and would remain even in a more modern architecture.
Thank you. Any further question from the audience?
Hello, Sean. Thanks
Yeah.
for thanks for Professor Shi to ask the question for me. And for myself, I wanna ask about the kernel features of real time. Since I see in the slides that now the Red Hat Edge operating system provide the preempt RT patch to enable the real-time features. I want to ask, despite this, does it provide any other mechanisms to help the applications to enable the real-time?
So let me rephrase what I think you're asking, and you can tell me if I got it right. It sounds like you're asking, I highlighted preempt RT. Are there other features that we're looking at that provide even more real-time like features? Is that correct?
Yeah.
Okay, currently no. From what we have talked about with the customers we're interacting with, it really falls into the situation we described in the previous question, that when they really want hard real time, they're going to want that, and we're not going to be able to bring Linux to that. And when they don't need that, but they need better preemption capability because they have critical workloads that aren't really real time, then the preempt RT patch set is sufficient so that they can run it on Linux. But there is still some level of architectural selection of where they want to run the workloads, and an expectation that within the overall automotive system, they're going to have something that still is real time for those elements that need to be. For example, you probably don't want to be operating your braking system off of Linux because it's not going to be real time enough for the reaction times you're going to want for something that is absolutely as critical as that and would need to be ASIL D. So we're talking about Linux being ASIL B. And so that alone negates some of the overlap in where the real-time and super safety critical elements wouldn't need to coexist, because they architecturally, if we're only ASIL B with Linux and you need ASIL D for this braking system, it's going to go somewhere else anyway. And so that's why we're not too concerned about elevating Linux to the higher level of capability, because we don't think the system architecture needs it today, because we're not going for complete integration. We're going for better consolidation in integrating, but not complete. And hopefully that makes the difference more clear. But I'm happy to go on if you'd like clarification.
Okay, thank you. And another question. For you mentioned that the operating system is software defined, and I know that a software defined network usually needs special devices. For example, the switch that supports open flow protocols. And I want to ask for the software defined operating system, does it need some special hardware, or do you plan to support or design a new device for this operating system?
So I will say software defined is a bit of a buzzword that gets overused, and I'm obviously guilty of that in trying to connect it to the industry trend of calling it the software defined vehicle. In my previous automotive semiconductor space, I was working in software defined radios, which is much more like what you were describing, where instead of having purpose-built bespoke hardware that you're using DSPs and other general purpose hardware in order to use software to perform the same functions. Our intention is not to do the latter, where we would say networking is now software-defined networking, and we're going to have traditional networking hardware connected to these SoCs. The software-defined aspect is, instead of as much of the vehicle being discrete hardware components, it's central compute with separate segmented hardware or software elements. That's what makes it software-defined from an industry buzzword standpoint. So I can see where you kind of said, "Oh, software-defined, that's amazing. You're going to do all these extra things in software." No, I'm guilty of misleading you by way of the buzzword. It's not to say that I don't expect software-defined hardware elements to be more prevalent in the vehicle over time. As I mentioned before, working in software-defined radio, like we had DSPs that were still somewhat custom built, but had changeable software to change which radio protocol you might want to use, moving towards general purpose SoCs that would have the DSP code entirely implemented there. So I do think truly software-defined things will exist in the automotive context, but I will clarify that is not what the in-vehicle operating system is trying to evolve. We're still connecting to standard computing components, again, trying to bring the data center elements into the vehicle, and so that is going to look more traditional.
Okay, thank you.
Okay, any further question from the audience? Safety? Okay.
Yeah, Dr. Shi, I have a question here. This is Jen.
Yeah, Jim from Wayne State. Yeah, go ahead.
Good morning, Sean. So I'm a researcher working in the real-time systems, real-time embedded systems. So since people have already discussed a lot in the real-time system, so I will ask some question else. So you give a very interesting talk about the software-defined vehicle. So currently we have some other software-defined device like smartphones, right? So in the smartphone, we also have the operating system, but it's evident that we cannot use the operating system in a smartphone to power an autonomous vehicle. But from your perspective, what's the key difference between the two? So because all the mobile devices, and what's the key difference from the operating system perspective?
Yeah, I think I'd say it's, I'll come to two, and another one might pop in my mind as I'm going. The first one is the need for functional safety is pretty clear. Like we can't avoid that need. The standard aside, we're going to need something that provides that level of risk mitigation. And that's not a concept that a consumer device like a smartphone has, nor do those operating systems have the level of process rigor applied to them, because they're like Android, for example, is, I would say, quasi open source. There are elements that are, but there's a lot of it that's not. And in order for our arguments about how open source, by way of its own processes, enables different safety arguments, that somewhat excludes those proprietary driven OSs from being able to make those same claims. It starts to be flavored more like, well, we have experts in our software because they wrote the software, and so we're just going to ask them. And you could argue that's how our high level argument could be sort of weakened or perverted by others that say, yeah, well, we're doing the same thing. It's just our code, not your code. But there is a distinction, and part of our responsibility in pushing the industry to accept these other ways of qualifying safety is to show those open source processes and then point the lens back on the others claiming they're doing similar things to say, well, show how you are having this broad rigor of different disciplines and people with different product goals observing the code before it even makes it into the repo. Like, oh, you're doing code reviews between two engineers on the same team. Great. We're doing code reviews across the entire world. Like the weight of that is a little bit higher. So that's one thing. I think the safety arguments are going to be harder to make on something like a smartphone. The other aspect is it doesn't carry quite the level of security and long-term supportability that's needed. And working in enterprise, we keep Linux. We have a 7-year standard life cycle with the option to extend for a given version of Linux that Red Hat provides. And for those mission critical systems like banking, like they are very reluctant to change anything because they're very concerned about security and things like that. But they also at the same time need to be able to accept updates rapidly. And so that level of responsiveness, that level of long-term viability and supportability is not a concern for consumer OSs, that they release a new version every year because people are getting new phones every year or 2 or 3. And why bother supporting a version of Android for 15 years? Because it doesn't make sense for that market, where we do that already in the data center because it's necessary. So translating that to automotive makes more sense because it's already got that maturity of life cycle that is necessary to be able to be in a vehicle for the lifetime of that product.
Yes, makes sense. So I'm more interested in the safety part. So
sure.
Maybe as you have mentioned that in the vehicle, on the vehicle, so the software should be executed at the right time, right? So, but these features are not supported in the smartphones. It's not necessary for the smartphones, right? For example, if the vehicle drives through an intersection and there's a traffic light and it's red, but the function is correct. The function is works well, but it identifies the red light late, right? There's some accident may occur. So I would like to know what Red Hat have done on this. So how to guarantee the timing correctness. So to ensure the safety of the vehicles, of the software-defined vehicles.
Yeah, so I would say we haven't done it yet. That is something we plan to do. That until we reach our safety certification certificate point in our process, I will not say that we have done it yet. But the plan is to use a combination of the things I've described. One of the core parts of this is the freedom from interference argument. And so we want to be able to say you can have QM code that lives alongside ASIL code, and the QM code is unable to prevent the ASIL code from operating at its expected priority in order to service that need. So the preempt RT patch set provides the framework to ensure critical processes are going to happen, and this segmentation prevents a rogue QM process from starving the resources, corrupting the memory, preventing execution of the ASIL process. That's theoretical. What we need to do is prove that by way of the kernel isolation features we've shown here, or by way of a combination of virtualization and containers layered on top of it. We haven't answered that question sufficiently to say, well, here's how you do it. But that is what our intent is to find that. And we're exploring that today. So we just had a review with our assessor about some concepts that our internal experts said, here's the things we're going to do to prove that we have adequate segmentation and freedom from interference. And they said, yeah, that's nice, but here's a bunch of other things you've got to go answer. So it's an iterative process, as I said before. We haven't solved it yet, but we're confident that we can. But I can't tell you, oh, it's going to take this exact form. And that's why you're seeing we have lots of avenues that we're going to explore still. And maybe a year from now, I can come back and actually answer your question in a way that you can go implement something that provides true freedom from interference.
Yes, great. So I would like to mention that Dr. Shi and I working on the real-time safety certification for the vehicles. So maybe in the future we can collaborate on these topics.
Absolutely.
Thank you for your talk. Thank you.
We'll have that. Yeah.
Well, I think Dr. Shi may have some other meetings. So is there any questions from the audience? Okay, if there's no other questions, let's thank Sean and
Yeah.
very nice talk. Nice to meet
Thanks
you.
everybody. And I'll point you again if you're interested in looking at the actual code we're working with. Happy to point you at our automotive stream distribution. If you have follow-up questions or you're interested in collaborating on something, please reach out. We're eager in forming a community around this work. So happy to have you involved.
Thank you.
Thanks everyone.